So in the last lecture, we had talked about the details of light matter interaction in semiconductor structure, different semiconductor structures. We had talked about the direct and indirect band gap and why emission is possible only in direct band gap. Talked about energy conservation, momentum conservation, etc. And today we will look at how the basics of some LED structures. Even though we are saying it's an LED, the structure of a laser diode is also the same. The basic structure, the gain medium is similar. It's just that in laser diodes, we have some additional mirrors that needs to get fabricated. But otherwise, the material structure that gives rise to the generation of photons, the mechanism is the same between LEDs and laser diodes. So we know that typically it is a forward biased PN junction. So that is what is shown here. So what you see here is a P-type material and an N-type material. And there is a junction here. So here is where you will have your depletion region. So this is, I'm trying to draw the depletion region across the structure. And of course, you will have a metallic contact through which you will send your injection current. And the recombinations typically happen in the depletion region. And the width of the depletion region is 1 to 10 microns in most of the materials, semiconductor materials. Now, this kind of structure is called as homojunction. This is called homojunction because the material that constitutes the P-type and the N-type are having the same band gap. And because the band gap is the same, there is no possibility of confinement of the carriers, in the sense that when you send an injection current, the carriers are generated anywhere in this, within this width of the depletion region, and it can be recombinations can actually happen in a widely distributed fashion. So the issue with the this kind of structure is that, even earlier LEDs were made with this kind of arrangement, but the issue was that the recombination can happen over this entire depletion region. Of course, the width of the depletion region is decided by your injection current, dopant concentration, and so on, which is very inefficient way of generating light. It results in a very low internal quantum efficiency. So what is done is in a semiconductor structure, instead of a homojunction, what is done is typically a heterojunction is what is fabricated. Now, what is this heterojunction? Heterojunction consists of a double heterostructure. Now, what is a double heterostructure? A double heterostructure consists of a P-type and an N-type. Now, the difference is that you have a band gap EG1 and a band gap again EG1 on either side. But in between the P-type and the N-type, you generate, you basically grow a thin active layer. Now, this thin active layer, the thickness of this is about 0.1 micron, several orders of magnitude smaller than the width of the depletion region itself. And this thin active layer will have you choose the material such that the band gap of that material is smaller than Eg. Now, this results in two benefits. One is carrier confinement and the second is optical confinement. Now, I'll tell you what this means. So this is the band structure for this composite heterostructure. So you have the P-type material, you have the N-type material, and its band gap. So this line represents the conduction band, energy level of the conduction band, and this represents the highest energy level of the valence band. And in the P-type region, you have EG1, for instance, and even in the N-type region, it is still almost same as EG1. But the key is that in the active region, you choose a band gap that is lower than EG1, right? Now, when that happens, if you inject carrier under that condition, so let's say electrons are holes are injected from the p type, or the electrons are injected from the n type, what really happens is that the carriers which get trapped in the lower band gap region, you see there is a large potential well, because of which all the carriers get confined in this active region. So this is what we are referring to as the carrier confinement. Now, since the width of the active layer is much smaller, the density of carrier density becomes larger, and larger is our carrier density, larger is the possibility of radiative recombination, and hence this process of growing a material, a thin active layer between the p-type and n-type, helps in increasing the radiative recombination. Now, this also has another benefit, and the second benefit is optical confinement. So it turns out that in semiconductors that are transparent, larger the band gap, it turns out that the refractive index is smaller. So this is not by intentional design, but this is how it happens. It's a consequence of band gap. So larger is a band gap, smaller is a refractive index, which means that this lower band gap region, which is the active region, actually sees the higher refractive index. So the plot that you see in red, which is here, actually shows the refractive index profile across the semiconductor, and this small region, which is of the order of 0.1 micron width, this region has a higher refractive index, and you see this is the region where you have the electrons and the holes are recombining, and that's where the photons are generated. Now the generated photons are now trapped in a region of higher refractive index, and you know that when you the basic structure of an optical fiber or an optical waveguide is to have a higher refractive index when compared to the surroundings, so that the boundary conditions allow the light to be trapped in this high refractive index region, right? Later on we will see the refractive index profile of a step index fiber. This looks exactly like that. So you will have the optical mode which may get confined in this central region, and the optical mode might look like this. And depending on the refractive index contrast and this width, you could have a single mode operation, which means you could have only one transverse mode that can be supported by this structure. We will talk more about how to decide the whether one mode is supported or more modes are supported later on when we talk about optical fibers, but the idea here is that all the semiconductor emitting structures, whether it is an LED or a laser diode, typically now these days will have a double heterostructure, where you can say that this is like a cladding which has a lower refractive index, and you have a core which is the active region which is of higher refractive index and smaller band gap to achieve both carrier confinement and optical confinement. Now, how is this made possible? How is it that we are able to actually create a heterostructure and p-type and an n-type region with a desired band gap? So this is possible with the progress in the semiconductor industry, or in the material science, semiconductor material science research. It's very common to do what is called as band gap engineering, right? So we will talk about that next. So this is how the structure looks like. On either side you have the metallic contact, and then you have the gallium arsenide substrate. On one side you have n-type doping, and the other side you have p-type doping. So this is forming the p-n junction. But just before you allow these n-type and p-type materials to come together physically, you also do what is band gap engineering, which is you basically change the molar concentration of gallium versus aluminum on one side, and you also change so this is the N type and the P type, which has the same band gap Eg1. The molar concentrations on either side are the same. And here is where you have the active layer, where you change the molar concentration of gallium and aluminum so that the band gap Eg is now smaller than Eg1, right? So this is band gap engineering. So with the consequence that as a result of this, you have, for instance, in this, this is N type in this side. So you have injected electrons here. They get trapped in this region. The band gap here is in this P type region is larger, and hence you will have these electrons or electron hole combination that's getting trapped in this active region, this region that is sandwiched between the P and the N, and all the electron hole recombinations happen in this region. And similarly, the injected holes get trapped in this region, and the electron hole combinations actually happen in this active region. And as we discussed earlier, that's where the refractive index is. So this is the refractive index profile. So that's where the refractive index is higher, and you get optical confinement. So typical example for band gap engineering, for instance, is for the materials that are typically used are, 0.81 to 0.87 micron, which is again in the optical communication range of wavelengths. The material used is gallium aluminum arsenide. That's what is shown here. If you want to have emission at 1 to 1.65 micron, which is again 1.3 micron is a communication band, 1.5 micron is a communication band, optical communication band. So for those wavelengths, the material used is indium gallium arsenide phosphide. These are compound semiconductors, alloys made with semiconductors with varying proportions. You can't arbitrarily change the proportion. You have to also make sure that there is a lattice mismatch. So we'll not go into the details of all that. But all what I want to tell you is that, look, the band gap engineering is possible. So you can basically engineer this value of Eg so as to get a desired range of wavelength. Silicon is not used as a source because it is an indirect band gap material, right? So it is tuned with composition. So for example, if you want to take a compound semiconductor indium gallium arsenide phosphide with X molar fraction of molar concentration of gallium and Y of arsenic, with indium with concentration 1 minus X and phosphorus with 1 minus Y. Typically this X by Y equal to 0.45 is required for lattice matching. Otherwise, we will have strain developed in the lattice, and that is not conducive for optical transmission, emission. And so if I take, for example, this kind of compound, Y can vary between 0 and 1. Y equal to 0 would mean that it is just an indium gallium phosphide material. The band gap empirically can be written as this relation. So you can now work out, if I want a band gap of, let's say, 1.3 micron, you can now work out what should be the fraction of Y, and correspondingly you can work out what should be the fraction of X. So this is how one goes about designing the gain medium for whether it is an LED or a laser. Now, once I design such a gain medium, the next question is, what is the spectral width of the emitted light, right? What are the possibilities of spectral? So even though we say, okay, my band gap structure looks like this, right? And this is the band gap Eg, the separation Eg. So what should be the, what are the range of energies, or what are the range of frequencies or wavelengths that are possible from this structure? So that is a question we are asking next. What is the spectral width of the source? Meaning, what are the possible wavelengths that can be emitted from this structure once I have made this structure? So it is very easy to understand that, okay, so this is the energy level diagram or the EK diagram of the semiconductor structure. So here we are talking about the Eg of the active region now. So this outside P and N doesn't play any role now. The band gap of those regions do not play any role. It is just the band gap of the active region which will now decide all these the properties that we are going to do next. So, so as I said, this is the EK diagram, the energy versus momentum diagram. We know that the energy conservation and the momentum conservation both have to be satisfied. And the smallest energy difference corresponds to Eg, which means H nu minimum corresponds to Eg. And so the minimum frequency that can be emitted by this semiconductor is given by Eg by H. Right? So you can convert this into wavelength. So corresponding lambda in micrometer is will work out to be 1.24 divided by Eg if Eg is in electron volt. Now, how did I get this relation? I of course substituted the value of the Planck's constant and of course converted the energy in electron volt, and because Eg is usually represented in electron volt, so this is like a very quick empirical, this is really not an empirical formula, this is a quick relation that one can work out to find out what is the wavelength of emission given that I have a band gap of, let's say, 1 electron volt or 0.7 electron volt or so on. So that actually decides the smallest frequency. Now, assuming that you have an electron sitting in the valence band here, conduction band here, and a hole in the valence band exactly sitting at the edge of the band, they are recombining. But this is again lambda minimum, so sorry, mu minimum, so this must be the lambda maximum. Now the next question is, what is the shortest wavelength? What decides the shortest wavelength? For instance, can I have you have an energy level here. Now remember, this is a band structure, so you could have a continuum of energy levels here. So if I just look at energy level and a set of energy levels here, you could think of having an electron, for instance, you have an electron here and a hole here, and this can recombine and can give you an energy which is H nu, which is much larger than the H nu minimum corresponding to Eg. The question is, what is the largest frequency, or what is the shortest wavelength that can be emitted from the structure? Now, if you want to really go into the theoretical aspects of it, it is going to take a little bit more time. So what we are going to just do today is to tell you the results, intuitive results. Okay. So the shortest wavelength obviously can get decided by the highest energy level. What is the highest energy level separation between the electron and hole? That decides my shortest wavelength. Turns out that there is one more condition. It is not just that you need to have energy levels, you need to also have a large occupation probability, in the sense that not only that there should be energy states, there should also be a non-zero probability that an electron occupies this state and a hole occupies this state. Only then a recombination can happen. Right? So first is in the occupation probability, and it is not just the occupation probability of occupation of electrons in this state, let's say E2, and this state hole in this state E1. You should have a joint probability density. I mean, joint probability of occupation. Right? So what matters is joint probability. You need to consider the joint probability of occupation of this energy state E2 by the electron and the E1 by hole. Now, what decides the occupation probabilities? Now we know that electrons are fermions. So what decides this is your Fermi statistics. We will not go into the details of Fermi statistics. But I just want to tell you that the probability of occupation of an occupation of an energy state E, according to Fermi statistics, is given by this function exponential E minus EF divided by KT plus 1. Now let's not worry about remembering this or anything. Just to tell you that this number tells you the probability of occupation of an electron in an energy state E, where the Fermi energy is EF. Okay. Now, what is Fermi energy? Fermi energy is that energy state for which this probability is half, because when you put E equal to EF here, this probability just comes out to be half. Let's not again worry about these details. This is just to give you an intuitive understanding of what goes into deciding the shortest wavelength. The second factor is the density of states. It's not just that you need to find the probability of occupation, you also need to have states. Now, theoretically, as per definition, density of states is the number of states per unit volume per unit frequency that satisfies this energy conservation condition and momentum conservation condition. So this basically comes from our EK diagram. So this EK diagram, the shape of the EK diagram tells you whether this, momentum conservation means that this vertical line, the transitions should happen across this vertical line. So in this vertical line, do you have enough energy states or enough density of states is the question, right? So you need to, in layperson's language, we just need to say that we need to have enough states, and each state needs to get occupied. There should be a probability of occupation. So these are the things that will decide the longest, highest frequency or the shortest wavelength. It turns out that this occupation probability actually goes on decreasing as you increase the energy. I mean, that comes from here. That's why I gave you this expression. As your value of E increases, what happens is that the occupation probability actually decreases, and to summarize, it is decided by the spectral width is decided by the rate of spontaneous emission, which is again, as I said earlier, it is decided by the joint density of states and also the joint occupation probability. Without deriving, I will say that the spectral width is proportional to R0, which is a constant. So this is constant. And it's also proportional to square root of h nu by Eg, because when your Eg is, when your h nu is smaller than Eg, when your this is my Eg, when you obviously cannot have a photon whose energy is smaller than Eg. So this is taken care by here. I mean, this you will take only the positive square root number. So that is where this is coming from. And there is also an exponential factor here, which comes from the probability. So this Fermi energy probability gives you, Fermi statistics gives you this term, and the EK diagram gave you this term. And so your emission probability is actually square root of h nu minus Eg exponential h nu minus Eg by kT. Now, if I plot this, if I try to plot this function, how is that going to look like? Let's take a minute to visualize this. So I'm trying to plot the spectral width in the sense that the rate of spontaneous emission versus frequency. So I know that this graph has exists only when h nu is greater than Eg. So up to Eg divided by h, which corresponds to, let's say, nu naught, the plot, there is no emission. So if there is no emission, I should have something like, zero rate of spontaneous emission. It starts increasing, it's square root of h nu by Eg, it starts increasing. But what is this term doing? This term, as nu increases, this h nu minus Eg term actually increases, and exponential minus of that. So this particular term will make this whole number decrease. So which means as your nu increases, this rate of spontaneous emission increases because of the joint probability densities, but then it starts decreasing because of the occupation probability, lower and lower occupation probability. So what you will end up getting is something like this. It'll probably touch zero only at infinity, but it starts tapering down very, very quickly, right? So you will obviously, you can find out a peak. Now, how do I find nu max? The peak now can be easily derived because this is a rate. So this, you can maximize this function and find out which is that nu for which this function is maximum. So that will correspond to the nu max. And once you have the shape, you can also find out what is called as the full width at half maximum. This is what we are typically this is what we typically quantify whenever we talk about spectrum. What is the center? What is the width? The shape is not, you can't describe this as a Gaussian or anything. It is just a shape which is a sharp cutoff, lower cutoff, and it starts increasing very sharply and then it starts falling down. Remember, this is also a function of temperature. So it turns out that if you maximize this function, so how do you maximize this function? You find the derivative, first derivative, put that to 0 and find out the value of nu for which this first derivative goes to 0. That is h nu equal to Eg plus kT by 2. You can work this out. Full width at half maximum. So you find out the value of this function. So what you need to do is to find the value of this function at when this, so you need to find out those frequencies for which this value of the function goes to half. So that's how you will find the full width at half maximum. And the surprising thing is that this full width at half maximum has now nothing to do with the material. Irrespective of the material, you have it just depends on the temperature. It turns out that it's just depending on the temperature, and you can work it out for room temperature what it is, and it will turn out to be 11 terahertz. Okay, so it doesn't matter what kind of LED structure you pick, whether it is indium gallium arsenide, indium gallium aluminum arsenide, etc., etc. It doesn't matter what the EG is. The FWHM of the emission is actually 11 terahertz, which is very surprising. We will try to convert this into nanometer. How do you convert this into nanometer? So you start by saying C is equal to nu lambda, and you say that you want to know, so this is the width, so you want to actually calculate what is delta lambda. So you say lambda is C by nu, and so delta lambda is C by nu square delta nu. Of course, we will put a mod square here because as we know that as the width in the frequency increases, the width in wavelength actually decreases. So you substitute that, and you can, as a homework, find out what is that delta lambda. And what you can also, the other way of doing it is, lambda is, nu is C by lambda, or delta nu is C by lambda square delta lambda. Both should give you reasonably the same answer. The reason I wrote this is because it is interesting to see that as your lambda increases, which means that as you keep shifting to the as your lambda increases, which means as you keep shifting to the left, as nu decreases, so you're picking lower and lower band gap material. As your lambda increases, that's when you have nu decreasing, so the band gap is lower. What you will see is that the delta lambda, so what is delta lambda? So this is a constant, so delta lambda is equal to lambda square by C delta nu. So what you will see is that as your lambda decreases, your delta lambda also decreases. So as your curve shifts to the right and left, the width of the curve also keeps shifting. That's because it is the delta nu which is an absolute constant, and its width in terms of delta lambda is dependent on actual lambda. So that's something interesting. So you can try converting this to nanometer. The next thing to do is to find out what exactly is the optical power generated by the LED. This is a very simple estimate. You know that the injected current is I. Now current is rate of injection of charge. So the rate at which the charge is injected. So the rate of injection of the number of carriers would be I divided by Q, where Q is the charge of electron. Right? So this is the rate at which the carriers are injected into the active region. Now we want to calculate the optical power. So in the PN junction, if I say that h nu is the energy of a photon, so this is energy multiplied by the rate of generation of photons. So h nu divided, so this is h nu multiplied by number of photons per time. Number of photons per time is the rate of generation of photons. So N is the number of photons. That will be energy per time, joule per second. So that will give me power in watts. All right. Now, how do I know what is the rate of generation of photons? Rate of generation of photons is nothing but the rate of radiative recombination. So last lecture we talked about radiative and non-radiative recombinations, and we said that it is the radiative recombinations which are resulting in the number of in the generation of photons. So this is proportional to rate of generation of photon is nothing but the rate of generation of radiative recombination. And we quantified the radiative recombination through this internal quantum efficiency, right? So this is h nu times internal quantum efficiency times the rate of injection of carriers. So this is to say that of all the injected carriers, only a fraction eta internal will result in the radiative recombinations and so the generation of photons. So my power is very simple to calculate. It is h nu times eta internal, and I've already told you how to calculate eta internal, times the current divided by Q. So what is the consequence of this? I can say for a given structure, h nu is a constant, eta internal is a constant, Q is of course a constant. So the power is directly proportional to current. So this leads to what is called as the famous Li curve. Li curve is L actually stands for light intensity, but instead of intensity, we are quantifying this in terms of power. And this is I is the current. Now Li curve is something that characterizes all the semiconductor sources. So if I plot the optical power versus the current, what is that plot going to look like? I know that it is going to be like the equation of a straight line with a slope given by this h nu times eta internal divided by Q. And what is important to note is that when your current is 0, the optical power is 0. So it is a line that passes through the origin. The slope of that line is decided by h nu eta internal divided by Q. The question we want to ask is, okay, is this going to go on increasing as you keep on increasing the current? Actually, no. One has to also think that beyond a certain current, you would have depleted all the dopants, right? So there may not be any carriers to actually, there may not be enough dopant concentration to undergo the recombinations. So this, after a very large value of current, what can happen is this can flatten out. You can think that this is getting saturated, but typically you don't operate LEDs in this saturation. Now this Li curve is important because this is what distinguishes an LED or a laser diode from an LED, right? So if you are given a 2-pin device, the only conclusive test for finding out whether it is an LED or a laser diode is actually this calculation of Li curve. Later on in laser diodes, you will see that the same Li curve for a laser diode will show a threshold behavior. It is going to be 0 for some current, it will have a threshold current, after which it starts increasing linearly. Whereas in case of LED, you have to remember that the Li curve is a straight line until it of course reaches the saturation. So with this we will stop here, and then we will now continue in later.